In the last lecture, we discussed about IC engines and other things, and we have discussed working, different strokes, classification, application, advantages, disadvantages. Everything were discussed in last video. In this video, we are going to discuss about different parameters that is needed to assess or understand the performance of an engine. So if you want to compare two different IC engine or CA engine, we need some parameters. Based on that parameter only, we are going to compare two different IC engines. So those parameters like brake power, indicated power, frictional power, and different system, valve timing diagram, port timing, and different loading condition, mechanical, electrical loading, eddy current dynamometer, different systems, and different tests we will discuss in this lecture. So we will discuss each and everything in detail, because based on these things only we are going to assess the performance of an engine. So if you want to understand the specification of engine, we need to know what are all the parameters, and we have to assess those, understand those parameters in detail. That we will discuss in this lecture in detail. Thank you.
In unit number 3, we have discussed about internal combustion engines and its combustion in internal combustion engine. In unit number 4, we are going to discuss about performance of IC engines and subsystems in IC engines. Subsystem means cooling system, lubrication system, and fuel injection system. Those are all the subsystems in IC engines. We are going to discuss those components, those topics in this unit. Let us get into discussion. Performance of an IC engine. Generally, performance is, why performance needed means performance is needed to compare two different engines. If two engines have the same power output, to decide which engine is giving more power output, more efficiency, economy, to determine all those parameters, we need these things. To compare two devices, we need some basic parameters. Those parameters are nothing but performance parameters. We are going to discuss how to find those performance parameters for an IC engine. We are going to discuss one by one. Here I have listed out some basic performance parameter like mechanical efficiency, brake thermal efficiency, indicator thermal efficiency, volumetric efficiency, total fuel consumption, specific fuel consumption, mean effective pressure. These are all some basic performance parameter that is used to compare two different engines. Let us discuss each and every performance parameter one by one. Indicated power is nothing but ideal power developed inside any engine, that is termed as indicated power. It is almost equal to by burning of fuel. Each and every fuel will have some calorific value. If you are burning that fuel, you will get some amount of heat energy as an output. That is the indicated power is nothing but if you are burning a fuel, it will produce some amount of energy. That energy is termed as indicated power. So indicated power will be calculated by this expression. In this expression, P suffix mi is nothing but indicated mean effective pressure. Mean effective pressure based on indicated power. That's why it is termed as Pm is nothing but mean effective pressure. I in suffix is indicating this mean effective pressure is based on indicated power. Capital L is stroke length. In previous unit, we have discussed about stroke length is nothing but distance between top dead center and bottom dead center. Area is A is area of the cylinder. We know cylinder is circular shape, pi before d square. D is nothing but diameter of the bore. Bore or diameter of the piston or cylinder. Then small n is number of working cycle. The reason for using number of working cycle is in case of two-stroke engine, if the crank is completing one revolution, that constitute one cycle. In case of a four-stroke engine, the crank has to rotate two times. It has to complete two revolutions for one cycle. That's why n by 2 for four-stroke engine, n for a two-stroke engine. Then in the denominator we will have a 60. The reason for 60 at the denominator is 60 generally speed will be in a minute, revolution per minute. To convert that minute into seconds, we will divide this equation by 60. Z is nothing but number of cylinders, whether it is a single cylinder engine or two cylinder, three cylinder. Based on the given example, we will decide the value of Z. In some textbook, in the denominator, you can find 60,000. That is to convert watt into kilowatt. Then next one is, here you should substitute pressure in terms of, if you need power in terms of kilowatt, you have to substitute pressure into kilonewton per meter squared. If you need pressure in terms of watt, you have to substitute pressure in terms of newton per meter square. Then brake power, it is the useful power that is available in the crankshaft or flywheel. That is termed as a brake power. That brake power is used to drive the vehicle. So generally, if you take two-wheelers, engine is connected to rear wheel by chain drive. So that chain drive is connected in a crankshaft. You will have a flywheel. In the flywheel, you will have some arrangements for transmitting power from engine to the rear wheels. So that is the useful power output that available in the engine to do the desired work. That is termed as a brake power. Again, brake power is calculated by this same formula. In this formula, you hear PM P suffix MB, mean effective pressure based on brake power. That's why it is here you will have B in the suffix. Sometimes if you are using mechanical dynamometer, we will use 2 pi nt. That formula also used to calculate brake power of an engine. It is used for a mechanical. If you are using mechanical dynamometer, they will use 2 pi nt by 60, this formula. The T is nothing but torque. Torque is nothing but force into perpendicular distance. Force applied multiplied with perpendicular distance, that is nothing but torque. And frictional power. In engine, we have discussed basic components like piston, cylinder, valves, crankshaft, camshaft, everything. So if you have relative motion between two components, you will have friction. Let us start with a piston and cylinder. In between piston and cylinder, we will have some friction. Again, this connecting rod is connected to piston in the smaller end. In this place we will have some friction. Again, larger end of the connecting rod is connected to crank. In that place also we will have some friction. Then valve mechanism is having some friction. If fuel pump is used in the cylinder or engine, that also have some friction. So the amount of energy that is wasted to overcome these frictional forces, that is termed as frictional power. That is theoretically. If you want to calculate how much amount of power that is wasted in overcoming these frictional forces, if you are subtracting indicated power with brake power, you will get the frictional power. So the difference between indicated power and brake power, that is termed as a frictional power. Then mechanical efficiency means useful power out, the ratio between useful power output to maximum power developed inside an engine, that is termed as mechanical efficiency. Useful power is brake power, maximum power developed inside an engine is indicated power. So the ratio between brake power to indicated power, that is termed as a mechanical efficiency. So eta is used as symbol for efficiency. Eta suffix m is mechanical efficiency. Then mean effective pressure. Mean effective pressure is nothing but the maximum pressure the piston experiencing over a period of cycle. That is termed as a mean effective pressure. But during suction stroke and exhaust stroke, you will have lesser pressure. During suction stroke, air is entering at a atmospheric pressure. During exhaust stroke, air is entering at a slightly higher than atmospheric pressure, say 3 to 4 bar. So during suction stroke and exhaust stroke, the piston will not experience higher pressure. So we can say mean effective pressure is approximately the average of pressure that is acting at the top of the piston during compression stroke and power stroke. That is termed as a mean effective pressure most of the time. But in general, they will take a cycle, the pressure acting at the top of the piston throughout the cycle. So theoretically we can calculate mean effective pressure as work done by swept volume. Again, if we can define mean effective pressure based on two parameters, based on brake power as well as based on indicated power. If the mean effective pressure is based on brake power, that is termed as a brake mean effective pressure. If the mean effective pressure is based on indicated power, that is termed as a indicated mean effective pressure. We know how to calculate brake power and indicated power. Just now we have discussed the expression for brake power and indicated power. Then this is theoretically sometimes actual in laboratory. To find indicated power, they will use indicator diagram. So this expression is used to find mean effective pressure from the indicator diagram. They will have a spring constant, length of the indicator diagram. With the help of those data, they can easily find indicated mean effective pressure in the laboratory. Second expression is for laboratory purpose. Practically, theoretically we will use first expression. First expression will be utilized most of the time while solving the problems. Then volumetric efficiency. Volumetric efficiency is nothing but the actual quantity of air that is entering into the cylinder to the maximum quantity of air that can accommodate inside a cylinder. That is termed as volumetric efficiency. In exactly, if you want to define volumetric efficiency, means actual mass of air, actual volume of air that is occupied inside a cylinder to the swept volume of the cylinder. That is the volumetric efficiency. Then volumetric efficiency will play a major role if the amount of air entering into the cylinder is decreasing, means volumetric efficiency will decrease. If volumetric efficiency decreasing, means oxygen availability will be lesser. If you are keep on decreasing oxygen content in a cylinder, means combustion will not take place properly. Again, power output will decrease. So you should have higher volumetric efficiency for a better combustion. That is the impact of volumetric efficiency on performance of an engine. Then fuel consumption. Fuel consumption means the amount of fuel consumed per unit time, that is termed as a fuel consumption. Specific fuel consumption means for 1 kg of fuel in a per unit time, for 1 kg of fuel per unit time, if it is producing 1 kilowatt, to produce 1 kilowatt of power output by consuming 1 kg in per unit time, that is termed as a specific fuel consumption. So total fuel consumption by brake power, that is termed as a brake specific fuel consumption. Indicated specific fuel consumption means if you are finding fuel consumption with respect to indicator power, that is termed as indicator specific fuel consumption. BSFC means if you are finding specific fuel consumption with respect to brake power. Okay, then next fuel consumption is in layman terms we will tell it as economy. Economy means for given period of time how much amount of fuel it is consuming to produce 1 kilowatt of power output. That's what we will mention as economy, like that. Then brake thermal efficiency means brake power to heat supplied, that is termed as a brake thermal efficiency. Heat supplied is mass of fuel, that is fuel consumption into calorific value, that is the power supplied to the engine. Again, calorific value we have discussed from classes 12, class 10 to 12 we have discussed. Calorific value of any substance can be found from bomb calorimeter. With the help of bomb calorimeter we can easily find calorific value of the fuel. Then mass of the fuel consumed can be found experimentally either by weighted analysis or by with the help of burette. Then indicated thermal efficiency means the ratio between indicated power and heat supplied, that is termed as indicated thermal efficiency. Relative efficiency means if you are comparing indicated thermal efficiency with air standard efficiency or brake thermal efficiency with air standard efficiency, means that is termed as a relative efficiency. So by comparing these efficiencies we can easily come to an conclusion which engine will give higher efficiency, like that. Total fuel consumption we have discussed already, the amount of fuel consumed per unit time, that is termed as a total fuel consumption. Total fuel consumption per unit power output is specific fuel consumption. Again we have discussed about brake power. Brake power is the useful power output from the engine. With the help of that useful power output we will do the desired work that is needed, if it is a transportation or lifting a weight from ground to any floor, or cranes, moving cranes, anything. So with the help of the brake power or propelling a ship, everything comes under with the help of the brake power. With the help of the brake power we can do all these works. So we are going to find how to we are going to calculate brake power from each and every engine. For that they are giving some standard experimental methods. We are going to discuss those things. So with the help of the dynamometer we are going to find brake power of each and every engine. Here I have given some basic dynamometers. Starting with olden days we have used prony brake, rope brake dynamometer, hydraulic dynamometer, fan brake, electrical dynamometer, that is termed eddy current dynamometer. Nowadays among these dynamometers eddy current dynamometer is better one, which is giving exact brake power output of given engine. It is giving load exactly on the engine. So among these dynamometer, eddy current dynamometer is highly accurate one. Let us discuss one by one. Then rope brake dynamometer. First one is rope brake dynamometer. In engines you will have a flywheel. Flywheel is used to maintain load variations. Power variation will be there throughout the cycle in an engine. It will store the energy during power stroke, that will be given during remaining period of cycles, that is during compression and suction and exhaust. It will not have power output. During that period of time it will releases the energy that is stored in the flywheel. So along with the flywheel one drum is connected. Over the drum we will have a either rope or belt will be connected at the circumference of the drum. At the bottom of the rope we will have arrangements for adding and removing loads. So if you are adding the loads, the spring load indicator will give some deviations. So spring constant will be read from this indicators. So if you are applying load means this drum is connected to crankshaft. If the engine is rotating, the drum also will rotate. If you are applying load, the friction between rope and drum gives some resistance to the rotation. So most of the time the engine wants to maintain constant speed. We will test this type of dynamometer in a constant speed stationary engine. So during that period of time it has to maintain constant speed, but because of this external load added in the drum, the speed of the engine will decrease. To maintain the constant speed, the amount of fuel supplied to the engine has to be increased. By adjusting the fuel system, we can maintain constant speed, and we will take the readings that is needed to calculate brake power. We will keep on increasing the load. With the help of the engine is designed to give this much amount of brake power. We know the maximum brake power. Speed of the engine is known. We know how much amount of load that is going to add on the engine. With this data, we can easily calculate what is the maximum load that can be applied on a given engine. So you should not overload the engine. If you are overloading the engine, there might be a chances of seizing, engine damage, any one of the engine component will get damaged. If you are overloading the engine, it will not able to pull the load. So you should load the engine a maximum up to 95% of its full load while testing. So this is again, we know it is a mechanical loading, 2 pi and t by 60. Torque is nothing but load into perpendicular distance. W minus S means load up. W is load, S is spring constant value that is given in a, most of the time spring balance reading will be given in the problem itself. Then load and perpendicular distance is radius of the drum. Here you can see R plus R means capital R is nothing but radius of the drum, small r is radius of the rope, because that is the perpendicular distance for the given load. So most of the time students will not add this rope, that will give some smaller deviation in the value. So because the rope diameter compared to drum diameter, rope diameter is smaller, so that will not affect the result much, but you should add that value also. So diameter of the drum and diameter of the rope, that is the perpendicular distance for a rope brake dynamometer. Then Prony brake dynamometer, instead of adding rope on the drum, here we will have two opposing brakes. So if you are adding more weight, it is going to give more resistance to the rotation of drum. Then accordingly the fuel quantity will be increased to maintain the speed. So Prony brake dynamometer is almost similar to rope brake dynamometer. Only thing is, instead of adding weights on the rope, here you will have some arrangements like a lever and fulcrum arrangement. Here we will add weights. Here only thing is perpendicular distance is linear. Here diameter and all those things will not come into play. Then hydraulic dynamometer, again hydraulic dynamometer means with the help of water will be filled in a casing. with the help of water we will give some opposing resistance to the drum that is rotating in the direction of flywheel. So we will give some opposing resistance. In the same way we will find brake power output. In previous cases we gave mechanical resistance by direct contact. Here we will give resistance with the help of water. That is the only one difference from previous ones. Then measurement of frictional power. Again frictional power will be calculated by any one of these methods. Williams line method is with the help of data collected from, we will discuss one by one. Williams line is nothing but we will collect data from experiments. X-axis is brake power. We will calculate brake power with the help of those expression 2 pi nta by 60, and fuel consumption with the help of burette and stopwatch we can easily find fuel consumption. Brake power in terms of kilowatt, fuel consumption in terms of kg per hour. Then we will plot the graph in a first quadrant, and we will draw the curve, and we will extend the curve until it is intersecting negative x-axis. The point at which the curve is intersecting on negative x-axis, that point is brake power point. This method is found by scientist Williams. That's why this method is termed as Williams line method. This method is used for finding frictional power in CI engines. One more method used for finding frictional power in a CI engine is retardation test. Retardation test also used to find frictional power in a CI engines. Then Morse test engine means Morse test in SI engine only. Morse test can be done only on multi-cylinder SI engine, not in a single cylinder SI engine. So Morse test is carried out. First we will find brake power of all the cylinders. All the cylinders will be receiving air and fuel mixture. All the cylinder will produce power output. After producing power output, we will calculate with the help of those expression with a suitable dynamometer. We can easily find brake power output of all the cylinders. After that, we will cut down the voltage supplied to one cylinder based on firing order, because if you are cut down the voltage supplied to any cylinder, mean again balancing will be a problem. Based on the firing order of an multi-cylinder engine, we will cut down the first cylinder spark plug supply. If spark plug is not receiving voltage from the battery, it is not going to produce spark. If spark is not produced in the corresponding cylinder, you will not get any power output. So one cylinder will not produce power output, remaining 3 cylinders will produce power output. Again, after some period, we will calculate brake power. After some period of time, we will cut down supply from 2 cylinders. Then we will calculate power output from remaining 2 cylinders. Then we will cut down the supply from 3 cylinders. We will calculate power output from 1 cylinder. In this way, we can easily calculate frictional power from each and every cylinder. So this is a Morse test. Morse test will be utilized for a multi-cylinder SI engine. Then last term is heat balance test. So far we have discussed about efficiency, different fuel consumption, everything. Heat balance test is most of the time utilized in power plants. In a power plants, they will calculate efficient. They will draw the heat balance sheet. They will give some amount of heat as an input. Among the 100% of heat given as an input, how much amount of energy is converted into useful power output, how much amount of energy is lost in exhaust gas, how much amount of energy is lost in a cooling medium. Some unaccounted losses are there. Unaccounted losses means You cannot calculate those values, some radiational losses, convective losses, frictional losses. So these are all some unaccounted losses in a system. So they will mention everything in the form of sheet. So we these are all the terms you should know. We will discuss those terms. So first one is heat input means mass of fuel into calorific value, that is termed as heat input. So percentage means most of the time heat input will be 100%, and numerator and the reason is numerator and denominator will be same, so 100% heat input will be always 100%. Then useful work based on a given loading system, whether it is a rope brake dynamometer or Prony brake or hydraulic dynamometer or electrical dynamometer. Based on a given loading system, you can easily find brake power output. If you know brake power output, out of the heat given as an input, how much amount of energy is converted into brake power. Brake power will be the useful power output. So then with the help of this expression, you can easily find percentage of useful power output, Q, QBP by Q input into 100, that is termed as that is used to calculate energy that is converted into useful form. Then next one is heat carried away by cooling water. Mass of water, Cp of water is known 4.187. Water outlet temperature minus water inlet temperature, and that is giving heat carried away by cooling medium. Most of the time water will be used as a coolant. If any other substance is used, Cp value will be given in the problem. So here I have took water as a coolant, so that's why heat carried away by cooling water. Again we will convert the percentage of heat carried away by cooling medium, then heat carried away by exhaust gases, again mg cpg, temperature of exhaust gas minus temperature of air, because we are using air as a air is taken into the cylinder, so some air is entering into the cylinder, while leaving the cylinder it is moving as a burned gas. Burned gases will have combination of air and fuel, that's why it is termed as a TG. At the inlet you will have only air, the outlet you will have both air and fuel mixture in the exhaust gases. So again we will convert percentage of energy that is lost in a exhaust gas. Then unaccounted losses is the difference between heat input and summation of brake power, heat carried away by cooling medium, heat carried away by exhaust gases, that is termed as unaccounted heat loss. Then percentage of unaccounted heat loss means Q unaccounted by Q input. We should list out everything in the form of table. Item means items or parameters. Heat input, useful heat is brake power, heat carried away by cooling water, unaccounted heat losses. If you are adding everything, if you are adding Q useful, heat carried away by cooling water, heat carried away by gases unaccounted, if you are adding all these parameters, you should get Q input. If you are adding useful heat percentage, heat carried away by cooling water percentage, heat carried away by exhaust gases percentage, unaccounted heat losses percentage, you should get 100%. If these two things are getting satisfied means your problem is correct. Generally 30 useful power output, 30% lost in the cooling water, 30% will be lost in exhaust gas, remaining 10% will be in unaccounted heat loss. That is a rough estimate for a given any heat balance sheet. If you are drawing heat balance sheet for any system, 30 30 30, that will be the 30 QBP, 30% of Q cooling medium, 30% of hot gases, then 10% of unaccounted heat loss. So this is how you can check whether you are getting around these percentages or not. Okay, it doesn't need always 30. Most of the time it will be 30. Okay. With this we will stop today's class.